battery's working now. So before we start, a reminder, so I sent out an email with the invitation and the Zoom link for tomorrow evening's question and answer review session. It will be much better if you're able to view the review session that I posted the link to on Learning Suite prior to participating in that, because that will help you come up with questions. That taped review session basically contains an outline of all the topics in these 4 chapters, some helpful hints on the exam, as well as a description of the sorts of skills associated with each topic that you should be developing. So today we're going to finish our discussion of nomenclature, talk briefly about the physical properties of alkanes, and then talk about conformations, or the 3-dimensional shapes of alkanes, spending most of our time with simple acyclic alkanes, ethane and butane, and then introducing cycloalkanes at the end of class. So I've drawn for you an example, a compound, and I've numbered it for you, and I've given it a name. Okay, so the name should make sense based on the numbering. Remember, in the IUPAC alphabet, trimethyl comes before propyl because we ignore the tri prefix. But this particular compound has 2 different 7-carbon chains. So I chose the one that goes like that, but if I would have just kept going to the left, I would have also ended up with a 7-carbon chain. So why did I choose the one that went around a bend as opposed to the one that goes straight? Yes, please. More substituents, yes. More branches or more substituents. So one of the rules of IUPAC nomenclature states that when you have 2 different chains of the same length in a molecule, you choose the one that has the most substituents, or the most branches coming off. So this one has 4 substituents, 3 methyl groups and a propyl. If we were to take the other chain, we would only have 3 substituents. Okay? Any questions on how we came up with that? Yes? Then you probably won't encounter that because I don't know what you would do in that case. Okay? Other questions? All right, let's look at cycloalkane naming, which is similar but not identical to naming acyclic alkanes. So I'll draw for you our sample molecule. And then over here, we'll do the rules. So the name of a cycloalkane has almost the same format as the name of an alkane, prefix plus parent plus suffix. But we have to insert the phrase cyclo into the name, and the suffix is still going to be ane. Okay? So, first step in naming a cycloalkane, count number of carbons in the ring. So what do we end up with in our example? How many carbons in the ring? 6. So what is the parent name going to be? Cyclohexane. Okay, so the parent name, cyclohexane. All right. Now, the next point is where we name and number our substituents. And there are some differences in how we do this compared to acyclic alkanes. Okay? First point, no number is needed if there's only one substituent. Okay? So let's temporarily erase this group. What would the name of this compound be? Methylcyclohexane. Why do we not need a number? It doesn't matter. You could draw that methyl group on any of these 6 carbons, and you could call that methyl cyclohexane because it's all the same compound. It doesn't matter which of the carbons you draw it on. So we do not need a number to distinguish between different isomers in the case of a cycloalkane with only one substituent. But if we have 2 or more substituents, we do need numbers because there's lots of different combinations of locations for putting those 2 substituents. Okay? So, if we have to number, we're going to use the first point of difference rule, which we learned on Monday. And when we apply the first point of difference rule to cycloalkanes, the way we apply it is we number in the direction that gives the lowest number to the second substituent that we encounter. So we have to have a starting point. That starting point is going to be a location where we have a substituent because we want carbon 1 to have a substituent, so we have low numbers. And then we're either going to go clockwise or counterclockwise in whichever direction gets us to the second substituent at a lower number. If there are 2 equal possibilities, then we're going to alphabetize. We're going to give the lower number to the substituent that comes first in the IUPAC alphabet. Okay? So based on these principles here, what is the first part of the prefix for the name of this compound going to be? Okay, I heard a 1-ethyl out there. Does that sound good? Okay, we'll choose 1-ethyl. Forgot my dash, sorry. 1-ethyl. And then what's going to go next? 3-methyl. Okay. So we have a 1-3 relationship between these 2 groups. We could start at either one and then count in a direction that would give 3 to the second substituent. So 2 equal possibilities. We choose the one that puts the substituent that comes first in the alphabet at the beginning. Okay? Any questions on how we came up with that name? All right, let's look at a couple of other examples. Okay, this one is going to be very similar to the last one, except we're adding a 3rd substituent. What's our parent name? Cyclohexane. Which substituent, we'll ignore the numbers right now. Which substituent is going to come first in the prefix? Ethyl, okay? What's our other substituent? Dimethyl. And remember, ethyl comes before dimethyl in the IUPAC alphabet. We ignore all prefixes except iso, okay? So ethyl comes first. What number goes in front of ethyl? 3, okay? And then what goes next? 1,1 dimethyl. So why did we choose this as carbon 1 instead of that? Who can raise their hand and explain? Yes, please. Exactly. So it's important to remember that we don't apply the alphabet unless the 2 possibilities are equal. If we start here and name this carbon 1, then our second substituent is also at carbon 1. If we would have started here, our second substituent would be at carbon 3. Okay? So this numbering system is better, is the approved one for the IUPAC name. Any questions? Yes, please.
So in theory, if
So you're saying if we had another ethyl group here, then it would go to 1,1-diethyl. Yeah, but this particular one is numbered this way. Okay. All right, let's look at another one where we have 3 different substituents, but let's put them on different carbons. Okay. What's our parent name? Okay, this one is a cyclopentane. What are we going to put in front? We'll ignore the numbers. We'll do the numbers last. What substituent name goes in front? Triethyl. So this one, we had 3 of the same group. And then what numbers will go in front of that? 1, 2, 4. Very good. Okay. So in this particular case, it wouldn't matter which of these 2 you called carbon 1, but if you called this carbon 1, you'd have to go clockwise. If you called this carbon 1, you'd be going counterclockwise. Okay? Any questions? Okay, our last example will illustrate a principle that I haven't taught you yet. That principle is that if we have a ring, and then we have a chain attached to the ring, and the chain has more carbons than the ring, then we name the ring as a substituent of the longer chain. Okay? So let's do an example of that. What's the parent name? Pentane. Okay. So we're not counting any of the carbons that are part of the ring. We're only counting the carbons that aren't part of the ring, and there's 5 of them. Okay. Now, to name a ring as a substituent, we do the same thing that we did with alkyl groups. We're going to drop the ane and replace it with -il. Okay. So what is this ring as a substituent? Cyclopropyl. Okay. That is going to be a cyclopropyl group. And what number goes in front? Yes, this one will have a 1. So we haven't seen a substituent at carbon 1 before in a chain, because if it were an alkyl group, it would simply make a longer chain. But in this case, because it's a ring, and we're not counting it as part of the chain, we can have a cycloalkyl group at carbon 1 of a chain. We could have other groups that are not alkyl groups, like we could have a chlorine or a bromine or something like that, which we'll learn how to name later on. But this is the first type of compound we've encountered where there was a substituent at carbon 1. Any questions? Okay, so you now know enough to be able to solve any nomenclature question you'll see on an exam or a homework problem. So as I mentioned on Wednesday, I suggest that you practice, that you do the homework problems, but don't obsess over nomenclature. Don't try to come up with crazy-looking molecules with dozens and dozens of bizarre-looking substituents and waste a lot of time trying to name them, because that's not going to be a good use of your time. Another skill that you do need to have, though, is to be able to convert a name into a structure. The examples we've done in class have been structure to name, but you will see problems where you are given a name and you need to convert that name into a structure. And there are homework problems like that as well. Okay? All right. Let's talk briefly about interesting alkanes, naturally occurring alkanes. So there's 2 types of the most interesting naturally occurring alkanes. One is natural gas, mostly made of methane, about 60 to 80% methane. And then the remainder is ethane, propane, and butane, used as a fuel. A fact you might not know about natural gas is it is odorless. You might say, wait a minute, when I've smelled a natural gas leak, I've definitely been able to detect it. That's because they add a small amount of a really, really smelly compound that's not an alkane, known as methane thiol, to allow us to detect it. If we were not able to detect natural gas leaks, the result could be catastrophic. So it's important for them to add a small amount of a really smelly compound to natural gas to allow us to detect it. And then we have petroleum, or crude oil. And petroleum is a mixture of hundreds of different alkanes, ranging from 1 carbons. Well, that would be methane, of course. Methane can come in crude oil, but it's usually flared off at the site where they collect it. But technically, it comes out of the ground with the rest of petroleum. And then you have compounds with up to 40 carbons in that mixture. So before we can use crude oil, we have to refine it into usable fractions. We can't use that huge mixture of hundreds of compounds. And 3 of the most useful fractions of crude oil are gasoline. Gasoline contains alkanes ranging from having 5 carbons to 12 carbons in their skeleton. And then we have kerosene. Kerosene is the range from 12 to 16 carbons. And then we have diesel fuel, used to power trucks and some cars. And that's the highest of these 3 most usable fractions, I should say. Okay? So gasoline is the most valuable component of petroleum. So since oil companies are in the business of making money, they've figured out how to convert petroleum into as much gasoline as possible. They have 2 processes that they perform. One is called cracking. Cracking, as the name suggests, takes the longer chain alkanes and breaks them into smaller components. So you're taking out the higher molecular weight portion and generating more molecules in the C5 to C12 range. They can also perform a process called reforming, which takes the ones below 5 carbons and links them together. So by combining these 2 processes, oil companies can convert almost half of petroleum into gasoline. Okay? And then once they've done that, then they have to separate the gasoline from the other components of crude oil. And that's what they do in these big towers that you see at refineries. So you've probably all driven by refineries. If you've driven north on I-15, you've driven by one in North Salt Lake. And now you know that what they're doing in these towers is they're distilling refined crude oil to separate the different fractions. And as they pipe the crude oil through these different areas, they change the temperatures so that they can collect the different fractions. Okay? They up the temperature as you go down to distill off these other fractions. Fuel oil is going to be comparable to diesel. And then your engine oils that lubricate your internal combustion engines are going to be here. And the residue that doesn't boil is going to be turned into asphalt. Okay, so another interesting fact about petroleum is that the building blocks for virtually everything that is man-made are contained in petroleum. So anything that's plastic originated from petroleum. Synthetic fibers originated from petroleum. Pharmaceuticals or other consumer products, in most cases, originate from petroleum. Some of those originate from other natural sources, but most come from petroleum. Question? Yeah, there are some compounds with functional groups in them, so it's not just the long hydrocarbon chain. So you can fish out some of those other components, alcohols and so forth, alkenes, and you can use them as building blocks for these other things that I mentioned. Yes?
You said they get 47% into gasoline, but can't they take the ones, the diesel and all the higher ones and take them back through the cracking
They possibly could. I'm not. I must confess, I don't know if this number involved multiple cycles of cracking or if it becomes economically unfeasible to do that. I don't really know, but I got this number from a fairly reliable source, so we can basically conclude that almost half of petroleum is typically used to make gasoline. There is a movement to generate starting materials for plastics, fibers, and pharmaceuticals from renewable sources, because obviously there's a limited quantity of petroleum, and that movement is growing, but still a minority. So still today, the vast majority of products that are synthesized by humans originate from crude oil. So the price of crude oil controls more than just the price of gasoline. It controls the price of anything that's made. Yes? So plant material would be a great one. So if you could use cellulose or other kinds of plant material that are produced in plants that we don't eat, then that would be very useful. We don't want to convert plants that we eat into plastic. That wouldn't make much sense. But if we can take things that we don't eat and we can harvest them and replant them and convert them into plastic or fibers or things, then that's a good thing. So, all right. Let's talk briefly about physical properties of alkanes. What kind of intermolecular forces can we make between two alkane molecules? Van der Waals forces, exactly. So how would the boiling points of alkanes compare to other classes of compounds that had similar sizes? They're going to be lower. They're going to be small. So low boiling points with alkanes, because no functional groups capable of dipole-dipole or hydrogen bonding. Okay? Are alkanes going to be soluble in water? No functional groups that can hydrogen bond, no water solubility. We find this out every time there's an oil spill. Okay? So we have here a table. It's hard to read because it's kind of small and grainy, but it's in your book, and it basically summarizes what we just talked about in the last minute or so on physical properties of alkanes. All right, so in the remainder of the time we have, we'll talk about conformations of alkanes and cycloalkanes. We need to learn some vocabulary in order to do this. Okay? So the first vocabulary word we have, stereochemistry. Okay? Stereochemistry has nothing to do with sound or stereo systems. Stereochemistry is the study of the three-dimensional structure of molecules. Okay? And then another term we need to learn is conformations. So conformations are different spatial arrangements of molecules, or different spatial arrangements of a molecule that are related to each other by rotation about single bonds. Okay? So I have for you a model of ethane, okay, C2H6. And I'm rotating about the carbon-carbon sigma bond, carbon-carbon single bond in ethane. And as I rotate, I'm generating different conformations of ethane. How many different conformations are there of ethane? Infinite, exactly. There's an infinite number of angles, an infinite number of ways we could chop up 360 degrees. So there's an infinite number of conformations. There are two that are the most important that we'll spend some time talking about, but there are an infinite number. And then there's another term that we need to learn in conjunction with conformations, and that is dihedral angle. Okay? The dihedral angle is the angle between bonds on adjacent atoms. Okay? So, in this particular conformation, what is the dihedral angle between these bonds? That would be the bond angle, which is not the same as the dihedral angle. Bond angle is the angle between bonds on the same atom. Dihedral angle is the angle between bonds on adjacent atoms. It's 0 here. The dihedral angle in this case is 0. Okay? Now, if I rotate, what is my dihedral angle in this case? 60 degrees. Okay?
Sorry.
Yes.
I can't visualize where
Okay.
the lines are for that.
So we'll draw it on the board in something called a Newman projection that might make it clearer, but it's also good to make your own models. So if my eye is going straight down the carbon-carbon bond of this compound, the angle between these bonds is 0. They're eclipsing each other. If I rotate, now that angle becomes 60 degrees. Okay? So that's a dihedral angle. So, yes, another question.
Sorry, how did you know that you were supposed to look down the bond like that, and also if you were in a bigger molecule than like?
Because when I took this class, my professor told me that's what you do. So, in order to measure angles on adjacent atoms, you have to look down the bond that connects those atoms. That's the only way you could measure that. So there's a way that we look down an atom. The way that we draw looking down a carbon-carbon bond in an atom is known as a Newman projection. Okay? So what we have here is this big circle in the back. That's representing the atom that's furthest from your eye. Okay? And then this point right here is representing the atom that's closest to your eye. And so I've drawn the 3 groups that are coming off of the atom that's closest to our eye. And then here is where you draw the 3 groups that are coming off of the atom in the back. Okay? So if I put all hydrogens here, this is going to be a conformation of ethane that is called staggered. Okay? So in the staggered conformation, we have 2 different dihedral angles. We have a 60-degree dihedral angle, shown right here. And that 60-degree dihedral angle is referred to as gauche. So when you see the word gauche, that refers to a 60-degree dihedral angle. We also have a 180-degree dihedral angle. Right, the dihedral angle between this hydrogen and that hydrogen, and these hydrogens have to be on adjacent carbons. That's 180 degrees. That's referred to as anti. So when we see the word anti, that refers to a 180-degree dihedral angle. So these 2 hydrogens that I'm holding in my hand are anti to each other. These 2 hydrogens that I'm now holding are gauche to each other. Okay, questions? All right, so the staggered conformation, where we have these 2 dihedral angles, is one of the 2 most important conformations of ethane. The other one is known as the eclipsed conformation, where we have 0-degree dihedral angles. And we'll draw that one over here. That one's a little harder to draw because we wouldn't be able to see the hydrogens in the back if it was perfectly eclipsed. So we just kind of draw them off to the side a little bit like this. And when we see that, then we should have a picture in our mind that these groups that we're drawing are eclipsed with each other and have a 0-degree dihedral angle. Okay? So in an eclipsed conformation, we have our 0-degree dihedral angle. We also have 120-degree dihedral angle. That one doesn't have a name. So 0 is eclipsed. 120 we never talk about, so it doesn't have a name. All right. So let's look at ball and stick models and space filling models of the staggered and eclipsed conformations of ethane. Which one is more stable or lower in energy? Staggered or eclipsed? Staggered. Why? Who can raise their hand and explain why the staggered conformation is lower in energy? Yes, please. Okay. So you're saying the atoms are spaced further apart. If we look at this model, so I'm going to hold it sideways now. Is there much difference in the distance of the atoms from each other? No, not really. They're all pointing away from each other. So it's not actually the atoms, but what is further apart in the staggered conformation than the eclipsed conformation? What was that? I think I heard the right answer. Okay, the orbitals or the electrons in those orbitals, right? The bonds. The electrons in the bonds are further apart in staggered than they are in eclipsed. So in the eclipsed conformation, you have the electrons in the carbon-hydrogen bonds too close together. They're repelling each other, and that repulsion is increasing the energy of the eclipsed conformation relative to the staggered conformation. Okay? So there's another term that we need to learn. Let's write that over here. The term is torsional strain. So strain refers to anything that destabilizes or increases the energy of a molecule or a conformation. Okay? So torsional strain is an increase in energy derived from eclipsing interactions. And we know that that is caused by the electrons in those bonds that are eclipsing each other being too close together. Okay? So our staggered conformation is free of torsional strain because we have those electrons as far apart as possible. Our eclipsing conformation has the maximum amount of torsional strain, and every other conformation will be somewhere in between. Okay? So we can look at a figure, a graph, where we're rotating 360 degrees about the carbon-carbon bond in ethane. And the book has helpfully highlighted one of the hydrogens in red so you can see that hydrogen move as it's rotating. And they've made models of all the staggered and the eclipsed conformations. The two on the end are identical. We have 3 staggered and 3 eclipsed conformations as we rotate 360 degrees. And we see that the staggered are at the energy minimum and the eclipsed are at the energy maximum. And we see that there's 3 kilocalories per mole of energy difference between the staggered and the eclipsed conformations. So what that tells us is that for each hydrogen-hydrogen eclipsing interaction, or each time we have a carbon-hydrogen bond eclipsing with another carbon-hydrogen bond, that costs us 1 kilocalorie per mole of energy. Okay? Now, it turns out that we have approximately 20 kilocalories per mole of energy available at room temperature. So this barrier of 3 kilocalories per mole to rotate from staggered to eclipsed to staggered is nothing. At room temperature, we're seeing very, very rapid rotation about this carbon-carbon bond in ethane, and all of the conformations of ethane are accessible at room temperature. So if we were able to put a tag, if we had a bottle of ethane molecules, and we were able to put a tag on an individual ethane molecule and watch it, what we would find is that it would be rotating very rapidly about the carbon-carbon bond, and it would be sampling all of the available conformations. Okay? However, if we were able to take a snapshot of our bottle of ethane molecules, and we were able to see what conformation they were in at any given instant in time, the vast majority of those molecules would be in the staggered conformation. Because the laws of equilibrium tell us that the lower energy species is going to dominate at equilibrium. Okay? So that may seem contradictory, but it's true. Rapid rotation, a single molecule of ethane will be able to sample all of the available conformations. But if we could freeze all of our ethane molecules at a given instant in time, we would find that most of them will be in the staggered conformation. Okay? Any questions? All right. Let's look at a larger molecule. Let's convert our ethane molecule into butane. Okay? And what we're going to do in butane, we have 3 carbon-carbon bonds in butane, and the one that we're going to pay the most attention to is the central carbon-carbon bond, the one between carbon 2 and carbon 3. Okay? So here's my butane molecule, and this bond I'm holding in my hand right now is the one that we're going to be rotating about to generate our Newman projections. Let's take a look at this figure that the book has given us. So the first thing we notice is now instead of having 3 hydrogens on the group at the end, on each of our carbons in our Newman projection, we now have 2 hydrogens in a methyl group. Okay? So this is butane because it's 1, 2, 3, 4 carbons. Right? The circle in the back is 1 carbon. The point right here is another carbon, and each of these methyls is a carbon. Okay? So what this means is that now we're going to have 2 different staggered conformations and 2 different eclipsed conformations. There's going to be 4 different conformations that are important for us. We've started out with one that they're calling staggered anti. That's because the 2 methyl groups are anti to each other. The dihedral angle between the 2 methyl groups is 180 degrees. We can just call this anti for short. We don't have to call it staggered anti. Okay? Then we end up with what they're calling eclipsed if we rotate 60 degrees. We rotate 60 more degrees, we end up with a second staggered conformation that's not the same as our first one. In this conformation, the methyl groups are gauche to each other. So we'll call this staggered gauche, or simply gauche, indicating the 60-degree dihedral angle. We rotate 60 more degrees, and we end up with another eclipsed conformation. Unfortunately, the book is not distinguishing between these eclipsed conformations. I like to call this one fully eclipsed. The one that has the 2 methyl groups eclipsing each other, I refer to it as fully eclipsed. And then the one where the methyls are eclipsed with hydrogens, I refer to that as simply eclipsed. So you can just write fully here in front of this one. And then as we continue to rotate, we're just going to encounter the same ones we did before: gauche, eclipsed, anti. Okay? So let's take a look at another figure that gives us ball and stick models of the gauche and the anti conformations. Which of those 2 conformations is lower in energy? Okay, I heard anti from the audience. Would you be willing to raise your hand and explain why the anti conformation is lower in energy? It is correct, yes. Okay, so in anti, these 2 methyl groups are further away. In gauche, what you find is these 2 methyl groups are close together, and as you're rotating them, you can see these 2 hydrogens are going to get too close for comfort. And that's going to increase the energy of the gauche conformation. Okay? So that introduces a second type of strain called steric strain. Okay? So steric strain is an increase in energy that is caused by forcing atoms too close together. So if you look at the gauche conformation, the electrons are spread out. It's staggered, so the electrons are spread out, so we don't have torsional strain. But we have atoms that are forced too close together, so now we have steric strain. Question?
I don't understand the difference between steric and torsional strain. Isn't it, like you said, the atoms are closer together, but isn't it always the electrons that are going to be surrounding the atom causing the actual interaction?
Well, these are hydrogen atoms, and so it's more the nuclei that are getting close together because the electrons that hydrogen atom has access to are in the sigma bonds.
Okay, so steric would only be when hydrogen atoms are close together.
Usually it's hydrogen atoms, yeah, but it's nuclei. It's putting if the atoms are too close together, it'll be steric strain. If the electrons are too close together and eclipsing, it'll be torsional strain. Both raise the energy, but we do need to distinguish between the two types, the one that's caused by electrons and the one that's caused by the atoms or the nuclei. So we have here a similar graph to the one I showed you earlier. And we see that the anti-conformation is 0.9 kilocalories per mole, lower in energy than the gauche conformation. So that tells us that if we have two methyl groups gauche to each other, that's going to cost us 0.9 kilocalories per mole of energy. And that's due to the steric strain. Okay? And then we see that the fully eclipsed conformation is higher in energy than the eclipsed. Fully eclipsed is 6 kcals per mole higher than anti. And we already learned that when we have hydrogens eclipsing each other, that costs us 1 kilocalorie per mole. So how much does it cost us to have methyl groups eclipsing? That costs us 4. And you can see that when methyl groups eclipse, not only do we have torsional strain, but we end up with steric strain as well. So that's why it costs us so much more to have methyl groups eclipsing. And then over here, we have hydrogens eclipsing, and then we have a hydrogen and a methyl eclipsing. How much does it cost us to have a hydrogen and a methyl eclipsing? Do a little bit of math. So how much of this 4 kcals per mole comes from the hydrogens eclipsing? 1. So how much is coming from each hydrogen-methyl interaction? 1.5. Yep. So you have a little bit of steric. When we have this situation, you have a little bit of steric strain by bringing these two hydrogens too close together. Okay? So with butane, the same principles apply to with ethane. We can sample all the available conformations because 6 kcals per mole is much less than 20. But at any given instance, we'll find the vast majority of our butane molecules in that staggered conformation, and then some in the gauche, and very, very few in the eclipsed conformations. And the same principles apply to longer chains. Any acyclic alkane is going to prefer the staggered conformation to the gauche conformation in order to minimize steric strain. Okay? So we should be able to analyze the Newman projections of larger alkanes. So let's go ahead and get our eye clickers out and answer this question. So, which of the following is the least stable staggered conformation of 2-methylbutane? Okay. We have 5 staggered conformations here. We're looking for the staggered conformation that's least stable or higher in energy. You can go ahead and talk to your neighbors. And in order to solve this problem, you have to know what 2-methylbutane is. So this is an example of a type of problem where you have a nomenclature component as well as a conformation component. So go ahead, talk to your neighbors, come up with an answer. Pretty quiet conversations going on today. Okay, so now I'm hearing more conversation. That's good. Let's try to come up with our final answers in the next 20 seconds or so. Okay, there's another one. Okay, any more? Going once. There's another one. Going twice. Another one came in. All right. Okay, we'll go ahead and stop. Okay, first of all, which of these conformations represents 2-methylbutane? Okay, E is 2-methylbutane. Which other ones are? C and A. What about B and D? What are they? 2,3-dimethylbutane. Exactly. Okay. So we need to be able to convert names to Newman projections and vice versa. Right. That's an important skill to have as well. Okay. So once we identified the 3 conformations that were 2-methylbutane, which one? And these are all staggered, of course. So which one of those 3 staggered conformations is the highest in energy? E. Why? How many gauche interactions in E? 2. How many gauche interactions in C? 1. How many in A? 1. So it's the number of gauche interactions. The higher number of gauche interactions makes it a higher energy staggered conformation. Any questions? Yes? I have no idea where it came from, but somebody came up with it. I don't know the origin, but it is what it is. Okay? All right. Last thing, last couple minutes, let's talk a little bit about cycloalkanes. The key with cycloalkanes that's different from acyclic alkanes is restricted rotation. We talked about that a little bit on Monday. We have a new type of strain, angle strain, an increase in energy caused by the deviation of bond angles from their optimum values. I've drawn for you cyclopropane here. Each of these groups coming off of the ring is a hydrogen. What are the carbon-carbon bond angles in cyclopropane? 60 degrees. What do they want to be? They want to be 109.5. So we have a ton of angle strain in cyclopropane. That's manifested by looking at this figure here on the left. Because of that 60-degree bond angle, the sp3 hybrid orbitals do not overlap as much as they would if you had 109.5. They just overlap a little bit, and what you end up with is electron density on an arc between the carbons in the bond as opposed to on a straight line. So the carbon-carbon bonds in cyclopropane are weaker than most carbon-carbon bonds due to angle strain. Now, they're still much more stable than non-covalent species such as hydrogen bonds. They don't just fly apart, but they are less stable than other types of carbon-carbon sigma bonds. And that is due to the angle strain causing inefficient overlap of those orbitals. Okay? Let's look at this drawing of cyclopropane. What other type of strain do we have in cyclopropane? And try to, in your mind, make a Newman projection looking down one of these carbon-carbon bonds. What kind of strain would we have? Torsional strain, because our hydrogens are eclipsing in cyclopropane. So we also have torsional strain. So for cyclobutane, which has 4 carbons, we don't have to have all 4 of those carbons in the same plane. And in fact, one of them twists out of a plane and adopts what's known as a puckered conformation in order to relieve that torsional strain. Okay? So we have a 35-degree angle between the 2 planes in cyclobutane, one plane from these 3 atoms, one plane from these 3 atoms, 35-degree angle, and that allows it to relieve the torsional strain, but of course there's still angle strain. But is there more or less angle strain in cyclobutane relative to cyclopropane? A little bit less, roughly 90-degree angle versus 60. Question?
You said that there's 3 atoms in each plane.
1, 2, 3. So you have a plane defined by these 3 carbons. And then you have a plane defined by these 3 carbons. So these 2 carbons would be in both of those planes. But it's not one plane because one of those atoms twists or puckers. That's for cyclobutane, to avoid torsional strain. So on Friday, we'll discuss cyclopentane and then spend most of our time talking about cyclohexane. Hope to see you at our Zoom question and answer session tomorrow evening.